Hello and welcome to the subunit organic compounds from the main topic of molecules to metabolism. We're going to be going through some of the basic elements found in the human body all the way to what organic compounds are versus inorganic compounds, and we're going to finish off with a bit of a proof of how we can actually make a organic compound that's usually synthesized in the body, but how scientists like this guy Frederick actually synthesized an organic compound in a lab. So first off, it's quite a simple lesson today. It's quite a lot of facts that you can go and write down and learn. Most of the stuff in this lesson is pretty straightforward. And in the next series of lessons, we're going to go into talking about carbohydrates and proteins and lipids, the various different structures involved, and it's going to get a little bit more interesting as we go along. Let's get straight into it. So you've got these percentages that you need to go and remember of these elements in the body. There's 65% oxygen found in the body. This is the main component or the main element found. Then we've got carbon, which is 18.5%. Some questions will say, give the descending order of elements found in the human body. Descending, obviously going down the hill. Descending the hill, you would then give it in this order. If they said ascending, you obviously do it in the opposite way. 9.5% for hydrogen and 3.2% for nitrogen. Obviously, the symbols for these elements are O for oxygen, C for carbon, H for hydrogen, and N for nitrogen. We have some of the biomolecules that we are going to go into further detail in further videos. The biochemicals that we talk about in biology are carbohydrates, of course, things like potatoes, pasta, breads. Carbohydrates contain specific elements. They contain carbon, hydrogen, and oxygen. You need to know the ratio of hydrogen to oxygen in a carbohydrate molecule is generally 2 to 1. If you look at glucose, the reason I'm putting a 1 there is because if you look at a glucose molecule, C6H12O6, if you divide everything by 6, you will obviously get 1 is to 2 is to 1. Other types of carbohydrate molecules have a different amount of carbon, but the hydrogen to oxygen ratio is generally 2 is to 1. So if they give you some random, if give you a multiple choice question and they give you a whole bunch of different molecules and they say which one is most likely to be a carbohydrate, look at the hydrogen to oxygen ratio. And if it's 2 to 1 ratio, it's more than likely to be a carbohydrate. Brilliant. So let's get on to the next macromolecule. I'm going to be sort of all over the show in terms of space here. We have lipids. These are otherwise known as fats, sort of a more scientific word. They have the same elements found in them, carbon, hydrogen, and oxygen. We've got proteins. Sorry for the background noise. I hope it's not too bad. Proteins, carbon, hydrogen, oxygen. They also contain nitrogen. They also contain sulfur. And then you've got proteins. Sorry, not proteins. You've got a DNA molecule will have carbon, hydrogen, oxygen, nitrogen, and phosphorus. Not to be confused with potassium. K is for potassium, not P. A lot of students make that mistake. Organic compounds, a general sort of basic understanding of what an organic compound is it's a carbon-based molecule. So it's got carbon all over it, and carbon is the central atom. For example, if you have a look at something like methane, methane looks like this. It's got the chemical formula CH4. This is an organic compound. Why? Because carbon is central to this atom. Of course, there are hydrogens bonded to this, but you do get organic compounds that will have other elements in them as well. But the main point here is that it's a carbon-based molecule. Okay. Now, carbon itself, we need to talk about carbon. And I can go into the chemistry, but I'd rather not right now. Write a comment and maybe I'll do a video on a bit more of the chemistry of carbon. But carbon can have 4 bonds. So it's got 4 potential positions to put other things. In this example, we've put hydrogen. Of course, you can add carbon, which would then give another 3 possibilities. This bond belongs to that carbon, it belongs to this one as well. So now we can add things like, we could add an oxygen there, we could add a hydrogen there, we could add a nitrogen there. The options for carbon are plentiful. So that's the reason why it's such an amazing element, is because it allows, and you can write this up, it allows for 4 bonds. It allows for 4 bonds, which means it gives rise to complex variations of molecules. And of course, if you got complex molecules, you're going to get complex organisms. Like animals, like us as humans, we are very complex organisms. The reason why we are complex is because we have carbon as a central element to structural components in our body, as well as metabolic structural components, as well as metabolic activities, things like enzymes that help us speed up reactions. These enzymes will contain carbon as well, metabolic activities. Great. So, that's organic compounds, the basics of it. Inorganic compounds, of course, these molecules, let's just get a better heading going here, neaten things up. Organic, these are organic compounds, they contain carbon, and most often than not there'll be a hydrogen element bonded to one of the bonds of carbon. There are molecules like a diamond, for example, that's only bonded to carbons. This is still organic, even though there's no hydrogen. It's still organic because carbon is central to this atom, and that is something that I just wanted to mention. In inorganic, I'm just going to turn the page of my notes quickly. Inorganic, let's get the heading down. Inorganic, these are molecules. I like to have everything nicely done. These are molecules that don't contain carbon, molecules that do not, underline not, contain carbon and hydrogen. Important to say that as well, and hydrogen. So see this as one thing, carbon and hydrogen. An example of an inorganic compound. Can you think of one that's not going to be something that is central to an organism, a complex organism, something like H2O? This is not an organic compound, it's inorganic. Unfortunately, there are some examples of exceptions to inorganic molecules, exceptions to the rule. For example, don't know why there's an S there. For example, carbon dioxide, even though it's got carbon, it's still an inorganic compound. Another example, carbon monoxide. Another example, carbonate ion. Remember, an ion is something that has a group of elements that has a charge. This whole thing has a charge of 2- or -2. And then we've got bicarbonate ion over here as well. That's CO3-. So some exceptions to the rule. Another thing I would like to mention is that you do need to know that in the human body there are other elements as well. Of course, we've got things like calcium that we get from milk. We've got things like potassium that we get from bananas. We've got a whole bunch of other elements that are found in the human body. These are the main ones, but there are other elements as well. Let's see if I can get a nice picture of it. Here it is here. So other elements: calcium, phosphorus, potassium, sulfur, sodium, of course, from salt, chlorine from salt, magnesium, trace elements of copper, cobalt, fluorine. I think there's aluminium in somewhere in here as well. No, there isn't. Zinc. So just be aware that there are other elements as well found in our body. Notice there's no things like lead. There's no things like gold or silver. These are kind of obvious to me, but I hope they make sense to you as well. Okay, let's go back to our slides over here. Organic compounds, I I wrote the heading and I didn't even look at it. Terrible. Okay, now we're going over to this little picture over here. This is basically just the concept that back in the day, they thought that all organic compounds were only made by living organisms. So if you're a living organism, you make organic compounds. There is no possible way that you can make an organic compound in a lab. This guy disproved that theory, and he turned this ammonium cyanide, he turned it into urea. That's what this arrow means. And so the only thing you need to realize from this diagram is that it is possible to make an organic chemical without a living organism. So you can make it in a lab. That's everything that you need to know for this 2.1.1, this very first topic within our section on molecules to metabolism. Next, we're going to go on to carbohydrates, and I hope to see you there.